So we'll go ahead and start today by looking at our calendar. And we just finished test number 2, which means you have like a 1 class break before project 7 is going to be assigned, which is next class. I do have it on the table if you wanted to try to get a jump start on things, but project 7 will be assigned next class. Today we will talk about sequences. And in fact, the chapters 9 and 10 are going to look pretty much completely different from anything we've done this whole semester. We talk about sequences, and then the next, 8 or 9 classes, everything until the 3rd test is about this thing called series. And we've seen summation notation a little bit. We've done Riemann sums. We're going to talk about series for the next 3 weeks. It is a significant topic in our class. Okay. So that is the plan. You'll notice that between this class and next class is how long? Is a week. So this coming, you can just sit at any table that doesn't have many people at it. So this coming Friday is staff development day. There are no day classes. There are like 14 hours of meetings for some of us, but you guys will have a day off. Monday is Patriots Day. I moved to Massachusetts and I was like, wow, I thought they were big into football in New York, but no, here we have a day off. What's that?
Boston Marathon Day.
Boston Marathon. It's not on Sunday? Boston Marathon's on Monday? Huh. Who knew? So we have no classes, no day classes, Monday or Friday, so we won't see each other for a week. Let's go ahead and jump in. So that means that there's really nothing coming for a long time. I mean, we do have what? We have a quiz on April 24th, and I see here that Project 7 is also due April 24th. I thought I really did work to make it so there was never a quiz and a project at the same day. I'm going to have to look at the calendar and see if I can adjust something on there. But anyway, this is a ways away. Any questions about the calendar? Okay, so one non-calculus announcement. I have handed out this 10-point checklist for developing your career path. This was created by some folks who are working here on campus. In addition to the academics, we also have a lot of people really interested in job skill building and career finding and all kinds of good stuff. So this was a checklist that I just saw last week for the first time. I think it's great. I'd encourage you to read through. Each row has a different thing that you can do to try to head you or continue you along a path towards a career. And again, there are a lot of people here with a lot of good resources. So I'd encourage you to take advantage of them. Any questions on this? All right, so the packet is separate from this 1-page handout. So everybody should have like 3 different things that they gathered today. The checklist that we just mentioned, there's this 1-page handout with a chart on the front and then like a procedure on the back. And then there's the thick packet. Everybody has 3 things? So first of all, this chart right here is supposed to be page 1 of the packet, but because this chart I could only fit onto a page in landscape, and I know it is possible to put 1 page of landscape at the beginning of a regular portrait Word document. I had a nightmare of a time printing them last time I did this course. So I just printed this 1 page separate, but it's really the first page of the packet. It is going to be something you'll bring with you on the tests and the quizzes. It is also something that in 3 weeks I'm expecting we can look at this and really make a lot of sense out of it. Whereas right now it probably looks like a bunch of gobbledygook. It might be intimidating, but this is where we're headed, to try to understand everything that's going on in this table. So we will come back to 2 sheets. Yes. You do get 2 sheets to use on the quiz and the test. So the other sheet is the actual page 1 of the packet. It has to do with something called Taylor series. More symbols that maybe are a little bit intimidating, but we will get there. So you'll bring both of those pages to the test and the final exam, but we will come back to them as appropriate. Right now we start on page 3, sequences. We will go to Angus. Okay, thank you. Number 2, Richard. Okay, let's pause right there. So much of what we've done in Calc 1 and Calc 2 has been talking about continuous functions, right? Functions that exist everywhere. And here we are looking at a bunch of dots. You could plot a bunch of dots, and these things would represent a sequence. So it really is a change in course for us. So you can think of a sequence as an infinite ordered list. There's the sequence of positive odd numbers. You can also think of a sequence as being a function whose domain is the positive integers. So for example, we could say that this function takes the number 4 and sends it to 7 because 7 is the 4th positive odd number. We buy it? And I could say that f of 5 is how much? 9, because 9 is the 5th positive odd number. Now we've had a little bit of sequence damage up on the walls here, but there are parts of 4 sequences up on these walls. And you can see the top row is just counting what number you're on, and then the bottom row is really the heart of the sequences. It's the terms of the sequence. Okay, so sequences for us are going to go forever. You can see the 1, 2, 3, 4, 5, dot, dot, dot. We can call the sequence S and then use standard function notation. I called it here f of 5 is 9, but really you could use any letter there. So S of 2 is 3 because the second odd number, second positive odd is 3. But more common than using function notation is going to use notations where we include subscripts. So S sub 2 equals 3 is another way of saying the second number in this list is 3. Okay. Can you guys do number 3 here? We'll get Josiah to read. Okay, so let's try this with your neighbors. Okay, let's check in and see how we're doing. S of 7, the 7th term in this list is 13. What's another way to say S of 7? Is S sub 7. Okay, so the name of this sequence is S. The little subscript tells you which number in the sequence you're referring to, which position you're referring to. But the actual 7th number in this list is 13. We're almost always going to use that bottom notation, not the function notation. Okay, S sub 100 says find the 100th term in this list. What is the 100th term in this list? One vote for 199, agree, disagree? Good, okay. And so then what do we do in math is we try to generalize, and now we're going to talk about the nth term, a generic term in this sequence that we're calling S. Anybody come up with the formula here? 2n minus 1 says Dave, yes? What'd you guys get?
Plus n minus 1.
Okay, another group saw it this way. N plus, is it in parentheses, the second thing you said? Yeah, n minus 1. How's that? Same thing, right? Okay, great. This is the list of odds, which for some reason was called S. Take a look at this green sequence here. Can you guys in the back? Ernie, can you see it? Yeah. All right, so again, ignore the top row. That's just the counter. But looking at the bottom row, what kind of special numbers are in this bottom row? Those are the perfect cubes. So how about we call that list over there C sub n for cubes, C. And can you guys write down what C sub 8 is and what C sub n is? So you've got your list up there of the first, well, it's supposed to be first 20 perfect cubes. We're a little short today. Okay, so what is C sub 8? It's 512. That's the 8th number up there. And then if we wanted to come up with the general formula for C sub n, it's n cubed. Everybody good? So again, the n is just the index, it's the counter. Just like when we were writing sigma notation, you have a little counter there, something that would just go 1, 2, 3, 4, 5. Oftentimes we used I for the counter. But the actual number that we're interested in, C sub 8, is saying find the nth number in the 8th number in this list. Okay, what if we look at blues over here on the other wall? Again, ignore the top, just looking at the bottom. Can anybody figure out a rule for that one? Yeah, so there's a times 2 thing happening here, right? Angus. Also a powers of 2 thing. So let's see, so those are the powers of 2. I'll call it T because it has to do with 2. So let's suppose that we wanted to write down a formula for T sub n. So you want the nth term in that list. And it's 2 to the n. N is the number in the top, just telling you what slot you're in. And it's just 2 to whatever number is up above. Do we buy that? 2 to the 5th is 32. Okay, this thing right here is called an explicit formula because if you wanted to find the 30th number in the list, you just plug 30 into this formula and it spits out the answer, right? 2 to the 30. But sometimes we can't be so fortunate as to have an explicit formula where you can just jump to any number in the list at any time. Sometimes we're going to use something called a recursive formula. And folks familiar with computer science maybe have done a lot of recursion in their programming. So here's an alternative. Can you figure out a way to do something with the previous number in the list? That's what the n-1 thing represents, to get the current number in the list. That's the n thing. What do you do to the previous number to get the next number? Cole. Oh, you're gonna walk us through the proof. I just want the formula at this moment. Okay, so we do need to know what the first term is. In this case, what is the first term? It's 2. But now, suppose you're sitting at the number 64. How do you get to the next number? You multiply by 2. Does that work every time? If you're sitting on 128, how do you get to the next number? You multiply by 2. So then what we can do here is write this. This says, here's the formula for the generic nth number in the list, a current general number. This guy refers to the n-1 member, the previous one. So in math, this guy represents the previous term. And Tn is just our generic name for the current term. So that's the rule. You take the, if you happen to know a number in this list, you multiply by 2, that gives you the next number. You buy that? The downside with this kind of recursive rule is that in order to get the 30th number on the list, what do you need to know? You need to know the 29th number. But in order to get the 29th number on the list, what do you need to know? The 28th. So in order to get the 30th number, you'd actually have to build all the way from the first number, which is a 2, all the way up until you get to the 30th number. Clearly, if you have an explicit formula like 2 to the n, that's going to be way easier to get the 30th number. You don't have to build. But sometimes recursive formula is the best we can do. All right, coming down here to number 4, some notation. S1 is the first term, S2 is the second term, S sub n is the general term. And let's see, we talked about explicit formulas. And there's some general stuff. Let's move on to the next page. Let's try number 7. And we'll go up here to Andrew.
We also know how the sequence starts. First, a list of 4 terms for each.
Okay, so let's try this one together. All right, so the first one says that S1 is 1. That's the first term in the list, is 1. And then it tells you a formula to get the nth term. So let's list the first 4 terms. So the first term is easy, it's given, it's the number 1. If I want to find the second term, what I need to do is use the formula, the thing with the n's in it. But instead of n, what am I putting? I want to find S2. Yeah, we want to plug in a 2 for that n because S2 is the thing you want to stick in. So put n equals 2. And if you put n equals 2, then what does it say? It says it's equal to S what? If n is 2, what is this guy? S1. So that's S1 plus 2 to the, and again, how much is n? N is 1 in this entire row. So I'll just put that over here. You plug n equals 1 in, and we get that. So we plugged n equals 2 in. I apologize. N equals 2, and we get that. Thank you. So plug in n equals 2 into our most important formula for this problem is that guy right there. Everybody see where that last equation in blue comes from? And then S sub 1 happens to be known. It's right up above. It's 1. So this says 1 plus 4, and that's 5. Let's do another one together. To find S3, what value of n are we plugging in? N equals 3. So go back to that equation I circled in red. All the n's become 3's, and eventually you need to just get a single number as your answer. I got 13, is that all right? Okay, just go ahead and do one more. Find S4 for this sequence. Check in with your neighbors. All right, so it seems like the consensus is that S4 is 29. Any questions on that? Okay, can you guys do the same thing for part B? I'm looking for S1 up to S4, looking for the first 4 terms in this sequence. The first one is given to you, it's just a matter of copying it down. But see if you can work with your neighbors to find the first 4 terms in B. All right, 1, 2, 6, and 24, is that okay? Anybody recognize these numbers from another context? Are they what, Tassidy? Tassidy asks about perfect numbers. Anybody know what? Perfect numbers. What? Yeah. So perfect numbers are actually not open to interpretation. There is a math definition for perfect numbers. Tassidy, do you know?
The sum of the factors.
Yeah. That's right. So a number is perfect if the sum of its factors is the number. What's that? Integers is buried inside of the word factors, but I have left a space because we're going to add one little word in there. But for example, if we take a look at the number, I don't know, 8. Let's list the factors of 8. All the numbers that go in evenly into 8, what are they? 1, 2, 4, and 8. This has to do with summing all of the factors. What do you get when you add all these factors? 15. Is it equal to the number that we started with, which was 8? It's not. Is it ever going to be equal to the number that we start with? No, because? Yeah, because the number we start with is always in the list. Okay, so then we're going to add the word here in this blank. If the sum of its, I think the word is proper, actually, now that I think. What does it mean? All the numbers less than. I think the word is proper, but it says all the numbers except the number itself. Okay, now let's cross off the 8. What do we get when we add them up? 7, which is close to, but not quite equal to 8. So if the sum is smaller than the number you start with, then the number 8 is called deficient. It doesn't quite add up to itself. It could be the case that a number has a bunch of factors, like 24. Let's list the factors of 24. 1, 2, 3, 4. 6, 8, 12, and then we're not counting 24. Add them all up. Is it going to be smaller or bigger than 24? Much bigger, right? Okay, so 24 is called abundant because it has a sum bigger than itself as opposed to the deficient 8. Take a look at the factors for the number 6. What are they? 1, 2, 3, and then we don't write 6. What do you get when you add those? 6. Doesn't that feel nice? It's perfect. It's perfect. Yeah, so that's a great find. Is that yeah, so 6 is the smallest perfect number. There is another perfect number that has 2 digits. You'd imagine these numbers are few and far between. So we'll just leave it as a challenge for somebody who's interested in finding the. Oh, it's not, but Tassadee was on. I mean, like 6 is, and 24 is not far from the 2-digit number that is perfect. But it's a nice. That's a good question. I know precious little about perfect numbers, but there's been a lot of work done on them, and a lot of it is quite understandable. So I think this would be great if somebody could do a little bit of work and explain some more stuff about perfect numbers to us. Yeah, it is close to 24. Okay. Any other thoughts? Where have we seen these numbers before? 1, 2, 6, and 24. I'll give you a hint. It had to do with your favorite project of the semester. The gamma function was clearly your favorite project of the semester. What numbers did we see in the gamma function? Do we remember? It had to do, yeah, it was factorials. How much is 4 factorial? It means 4 times 3 times 2 times 1. 24. Those are the factorials. Yeah, and so you saw this list of numbers in the gamma function. 1, 2, 6, and 24. So in this particular case, it turns out we can come up with an explicit rule and factorial. But most of the time you can't do that. All right, let's move on to number 8. Where are we now? We'll go over here to Steve. Okay, so we saw convergent integrals. For example, what can we do here? We can do like 1 over e to the 2x between 1 and infinity. You guys remember we had that useful integrals for comparison list? This was one of them. Despite the fact that there's a graph here that has infinite area, well, that goes forever to the right. This is the graph of 1 over 2 to the x, 1 over 2x. 1 over, I don't know what I'm talking about. E to the 1 over e to the 2x. Yeah, e to the negative 2x is good. So even though, you know, as you sweep to the right, it looks like maybe there's a chance that there's going to be infinite amounts of area because we go forever, we saw that there's actually a finite amount of area over there. But there are other examples of graphs that look like that, like 1 over x, 1 to infinity. And what was true about the area underneath this guy? Yeah, the area underneath here turned out to be infinite, right? And what word did we use when the area was finite? Converge. And when the area is infinite, diverge. So it's the same words. They still mean the same thing. If you get a finite number, then we say that the sequence converges. If it goes to infinity, or some examples are going to actually have several different finite numbers that the sequence kind of oscillates through, then we say it diverges. So for example, if you look at the green numbers over there, which are our cubes, as n goes to infinity, n is the top row, what happens to the bottom row numbers? They get bigger and bigger, faster and faster. Does that sequence converge or diverge? That one definitely diverges. It goes to infinity if you let it go forever, right? So we want to know if we can find some sequences that don't go to infinity. So for example, s sub n equals x to the n. Let's see. So x is some number to be determined. For example, the blue list is numbers of the form 2 to the n. Yes? And what happens to those numbers as n goes to infinity? Also goes to infinity. But can somebody think of another number besides 2 that I could put right here so that it actually wouldn't go to infinity if I went forever? David? 0 is good. What's every term in this list? They're all 0. That converges. It's 0. Any other numbers besides 0? 0.5. If we put 0.5 right here, yeah, and if we raise that to bigger and bigger numbers, like 0.5 to the 10 and 0.5 to the 100, we know that that list of fractions is going to go towards 0. And in fact, any fraction is good. So as long as x is less than 1, like 0.5, then what will the sequence converge to? What will you get in the long run? You'll get 0. So the sequence converges to 0 if x is less than 1. We're not summing terms until next class. What's that? Equal to 1 is a special case which we're going to talk about momentarily. I want to say one more thing about this. Ernie said fraction, so I just said less than 1. So is it true for any x less than 1? Yeah, don't we have to stop someplace? Like if x was -5, that's too far. That's not what Ernie meant when he said fractions. So we're the terms of the sequence could be anything. They can be, yeah. So where should we cut this off? I said x is less than 1, but I got to stop it somewhere on the left. For greater than or equal to 0, does that work? Can I go any further than that? How about -0.5? If we do -0.5 to the nth, so the first term is -0.5, second term is positive 0.25, next term is -0.125, that's an eighth with a negative. I don't know, 0.0, what is it, 625? What do those numbers go to? They go to 0 as well. So we can get into the negatives, but we're going to stop it where? At -1. So we're just going to stick some absolute values around that. As long as x in absolute value is smaller than 1, which means that the x's you pick have to be close enough to 0, have to be within 1 of 0, then the thing converges, and it converges to 0. And diverges if absolute value of x is greater than 1. Yeah, Angus. It's just shorthand. Yeah. Yeah, you could just as well write -1 less than x less than 1. Same thing. Okay, Dawn raises a good point. If x equals 1, then we're looking at 1 to the n. What is every term in that sequence? 1. Does it converge or diverge? Converges to 1. It's always 1. So if x equals 1, then s sub n goes to the number 1. It converges to the number 1. What if x is -1? -1 to the n. The first term when n is 1, what is that? Yeah, what's the first term? Yeah, first term when n is 1 is -1, right? -1 to the first. How about -1 squared? 1. -1 cubed? -1, 1, -1, etc. So here it's bouncing back and forth between two numbers. Do you guys remember way back at the start of Calc 1, we talked about limits? And if on the one hand, one side went up to some number, but the other side of the limit went to a different number, what did you say about the limit? It didn't exist, right? For us to say we have a limit, we need to approach a single thing. At least that's what we said in Calc 1. That's still what we're going to say in Calc 2. This diverges. So up here in parentheses, it says, as long as you approach a single finite limit. You can't approach 2 or 3. You can't cycle around. You really have to pick a number and head towards it eventually. So this guy right here diverges. Yeah, we could not do a sum for that either, because the sum would also bounce back and forth. Okay, 1 over n to the p. All right, what's going on here? Let's see, n is still the index, the counter. P is the number that we're going to have some freedom with. So let's just pick a number here. For example, 1 over n squared. So I'm picking p equals 2 in this case. If n is 5 or 10 or 100, what happens to that fraction? Goes to 0, right? Okay, what about 1 over n to the 7th? If you pick 5 or 10 or 100 for n, goes to 0 even faster than before. So I'm starting to feel like anything is going to head us to 0. What if we try like a fraction? Maybe I'll write it as a fraction. 1 over n to the half. What does a half mean as a power? Square root. Still going to 0, because the square root of a million is still a pretty big number. And that thing at the bottom will get big enough. So does everything just converge to 0? What kind of numbers can I put down there that are bad? Negative numbers. Because if you have 1 over n to the negative 3, what is that really? That's really n to the 3. And if you plug in a big n, you're going to get a big answer. You'll get a green answer, right? So what's the good case here? It's going to converge if p is what? Greater than 0, right? Any positive number means the n is really downstairs, and it will go to, the whole sequence will converge to 0. And I'm really not sure why I didn't include the counterpart to this, so I'm going to add to this sentence. Diverges if what is true? If p is less than 0. Like negative 3. Okay, so just like we had our useful integrals for comparison, here are 2 useful sequences that we're going to want to know the results of. They really are different things, even though in both cases we converge to 0. How are they different? 2 to the n is what kind of a thing? Like if you describe that as a function, what kind of a function is that? That's an exponential function, right? Because the variable n is in the exponent. But down here, n to the 3 is what kind of a function? That's called a power function. The variable is downstairs. So they really are different, right? One of them, the variable's upstairs. One of them, the variable's downstairs. Okay, so let's see if you guys can do number 10. We'll go to Tassiday. Thank you. I'm going to ask you guys to also list the first 3 terms. Anytime you see a new sequence, just to get a handle, just to play with some concrete numbers, list the first few terms of the sequence. So go ahead and list the first few terms of each of these and then chat with your neighbors and see if you can convince yourself that the thing converges or diverges. Let's do that for all 4 parts here.